Hello everyone, welcome to lecture series on M3 subject. For more videos, check in my playlist. So in our today's video, we are going to solve general solution or complete solution for our given linear differential equation. So these questions are very much important for you all guys in perspective of your Savitribai Phule Pune University exam, okay, SPPU exam. Okay, so without further ado, let's get dive into today's example. So here we can see we have example, find the general solution, okay, and d square y by dx square plus 3 times dy by dx plus 2y which is equal to e raised to x, okay. So this one is our given linear differential equation, okay, second order linear differential equation. And question, it is very much important, asked in SPPU December 10, December 2010, December 2016, December 2017 and May 2011. These many times this question repeated in your university question paper. So similar type of the questions are going to come. Similar type of the questions are going to come in your upcoming exam. So get ready for such examples. So let's get start our solution for this example. Now you see that we want the general solution. Whenever we say general solution, what first thing need to come in front of us? Okay, general solution, when we say, first thing we need to remember complementary function and particular integral. Okay, general solution can be written as complementary function, okay, plus particular integral. Okay, general solution can be written as complementary function plus particular integral. So work for complementary function right now. Okay, so for finding the complementary function, okay, for finding the complementary function, we convert our given differential equation into the some type of the auxiliary equation. Okay, let's convert it. Then what we have here, d square y by dx square. So we write its auxiliary equation for CF. Okay, for complementary function, we write d square for complementary function. So this one is an auxiliary equation. Okay, this one is auxiliary equation. So we write d square plus 3 times d plus 2 which is equal to 0. Okay, this one is the auxiliary equation. Why we go for the auxiliary equation? Because we want the roots. Okay, we want the roots in order to find out the complementary function. Okay, now see that we have the roots here, d square plus 3d plus 2 which is equal to 0. Now you can go for using directly standard result. Okay, what is the standard result? That minus b plus minus b square minus 4ac upon twice of a. Okay, you can apply that result also, but in simple such examples you have to find out the two numbers, their multiplication is a 2 and their addition is a 3. Okay, so we can see that minus 1 multiplied by minus 2, we write it as the 2, and minus 1 plus minus 2. If we go for this one, no need to take negative, we can take directly positive number. Okay, multiplication of plus 1 plus 2, we get the 2, and plus 1 plus 2, their addition is a 3. Okay, so how I'm going to write this one, d square plus d plus 2d plus 2 which is equal to 0. I written that 3d as a d plus 2d. Okay, so take d common from here, under bracket we left here the value d plus 1, again 2 common here, d plus 1 which is equal to 0, d plus 1 again common from these two terms, again d plus 2 which is equal to 0. Okay, these are the terms we found here. So what is the value for two different roots, d which is equal to minus 1 and d which is equal to minus 2. Okay, these are the two different roots we found here for our auxiliary equation. Then it's a complementary function, we write CF as, so complementary function. Okay, for complementary function we know that these roots are distinct and real. Then complementary function we write c1 e to the power m1x plus c2 e to the power m2x. Okay, so c1 e to the power m1 is the minus 1, this one is m1 and this one is m2. Okay, so e to the power minus 1 minus x plus c2 e to the power minus 2x. Okay, this one is our complete complementary function. So if you're going to write this solution, you will get the at least half marks for our example. Okay, so let's go for the particular integral. Now we're going to find out the particular integral, as we have right hand side which is a non-zero. Okay, so for finding the particular integral, okay, we are going to proceed here with the particular integral. So we want the particular integral. Okay, so first of all, we know that the particular integral can be written as 1 upon f of d into phi of x. 1 upon f of d into phi of x. Now we have to find out the f of d and phi of x. So see that this one is the we have a right hand side that we consider as the phi of x, and f of d here we have d square plus 3d plus 2 as a f of d. Okay, so replace these values here in our particular integral. So we write this one as 1 upon d square plus 3d plus 2. Okay, d square plus 3d plus 2 into phi of x. What is the value for phi of x? E raised to x. Okay, e raised to x. Now see that already we have learned 2 to 3 result in a particular integral. Okay, which results we learn in our particular integral? Let me show you all again. So see that these 3 results we derived in our previous lecture. Okay, 1 upon d phi of x, which is equal to integration of phi of x dx, 1 upon d minus of a phi of x, and 1 upon d plus of a phi of x. Okay, so we have to convert our given solution in one of the form. Okay, whether it is a0, a non-zero, a negative, or a positive. Okay, so we have to convert in one of the form. So let's see how I am converting here. Okay, so now see that we have 1 upon d square plus 3d plus 2. So particular integral can be written as particular integral which is equal to particular integral 1 upon d square plus 3d plus 2. So we cannot keep that one as it is, because as we have denominator 1 upon d plus a, d minus a, so take this one. Okay, d plus 1 and d plus 2, these are the factored form. Okay, take this one as a part of denominator. Okay, actually d square plus 3d plus 2 and d plus 1 into d plus 2 both are the equal. Okay, actually this one is the extended form of our given auxiliary equation. Okay, so I'm going to replace d square plus 3d plus 2 as a d plus 1 into d plus 2. Understood how I have written? Okay, let me explain one more time. Okay, so d square plus 3d plus 2, the value for d square plus 3d plus 2 can be written as d plus 1 into d plus 2. Okay, so that the value I replace here and write down e raised to x. Okay, that phi of x keep as it is. Okay, now we are going to solve this one as we have d term present here. D means it is a differential equation. Okay, and that we don't want here. So we have to take it out and need to find out the particular integral in some form of the polynomial equation, some form of the equation. Okay, so we are going to remove this one. Okay, we are going to remove this one using some standard result. Now see that we can write 1 upon d plus 1 into d plus 2. Okay, that means 1 upon d plus a into phi of x. Now see that I converted our given particular integral as 1 upon d plus a into phi of x. Okay, and what we have the standard form for 1 upon d plus a into phi of x use. We are going to use here, what we are going to use here, 1 upon d plus a. We are going to use here 1 upon d plus a into phi of x. Okay, so we are going to write 1 upon d plus a into phi of x as a raised to minus ax into integration of phi of x into e raised to ax dx. Okay, so if you don't know how these results coming from, okay, where from this result come, okay, so you must have to check my previous lecture. I explained everything how these results are coming. Okay, yes. Now see that compare this particular integral with this form. Okay, so right now we have 1 upon d plus 1 and d plus 2. These are the two multiplicand factors. Okay, so take one of the factor outside here, remaining one multiply here. Okay, so we write a particular integral. Okay, we write particular integral as 1 upon, so what we do, take one of the factor outside here. Okay, so which anything you can take, or you can take 1 upon d plus 1 outside or 1 upon d plus 2 outside. Okay, so it is completely up to you. So I'm going to take 1 upon d plus 2 out here. Okay, 1 upon d plus 2 out here. So under bracket it remain, what we remain here, 1 upon d plus 1 upon d plus 1 into e raised to x. Now see that what I have done, I converted our given f of d plus 1 into d plus 2 in this result. Okay, now see that 1 upon d plus a, that means 1 upon d plus 1, and phi of x which is equal to e raised to x. So replace these values here in our result. Okay, and keep that 1 upon d plus 2 as it is to his original position. Okay, yes, so I'm going to keep 1 upon d plus 2 as it is here. Okay, we are going to keep here 1 upon d plus 2 as it is, and 1 upon d plus 1 e raised to x. So that means phi of x is equal to e raised to x, and a which is equal to 1. Okay, compare this one with this one. So a which is equal to 1, that means d plus a which is equal to d plus 1. So a goes to be the 1, and phi of x it is here as e raised to x. So replace this value here, e raised to minus x. So we can write e raised to minus x, and value for a which is here 1. Okay, let me write a which is equal to 1 using this, and phi of x as a e raised to x. Okay, after comparison of these two values here, I got these two values. Okay, yes, so 1 upon d plus 2. Okay, 1 upon d plus 2, keep that one as it is. Okay, e raised to minus x, and the value for a is 1, so keep e raised to minus x as it is, because a which is equal to 1, so we don't need to write that a as 1. Okay, so integration of phi of x. Phi of x means replace this value e raised to x. Okay, so phi of x I replaced here. Okay, and e raised to x a is 1, that means again e raised to x dx. Okay, this one is complete. As we don't have constant term present in our particular integral, so you no need to write plus c again. Okay, because already we have seen that a particular integral do not contain any constant values. Okay, yes, let's go for finding this integral. Okay, now see that it looks quite confusing for us that to find out integral. Okay, now it is a function to the power function. So try to remember some old result. Okay, whenever we have function to the power function, then we consider as a substitution method. I know that you all are familiar with that substitution method. So we are going to apply substitution method here in order to solve this integral. Okay, so which value we have to substitute here? Now see that function to the power function. So whatever the value we have function to the power function, that means this function consider as some value. Okay, so I'm going to consider e raised to x as a t. Okay, I'm going to consider that numerator power part. Okay, e raised to x as a t. So why I consider e raised to x as a t? It is quite difficult to integrate or to differentiate or to solve function to the power function, function divided by function. So these are the quite complicated form. So in such a case, you have to apply substitution method. So we are going to consider e raised to x as a t. Okay, now see that if you are replacing this value, so we are working under this integral, you don't have to take that e raised to minus x, because this one is already out of the integral. So we don't have to worry about e raised to minus x. We have to get worried only with this integral, and we have to remove that integral from here and get your regular terms. Okay, so that's why we are going to replace all these values from under integral. So I consider e raised to minus x as a t, and wherever you found x or dx term, replace also them. Okay, we just are not going to replace only e raised to x, this one. Okay, so I consider e raised to x as a t. Okay, that means it goes to t, it goes to t. But what about for dx? Dx is the also term in the term of x. Okay, dx is the also term in the term of x. So we have to replace dx also. So see that very carefully how I'm going to replace dx. Okay, so differentiate both of the sides. E raised to x dx by dx, which is 1. Okay, then we write a dt by dx. That one I'm going to differentiate further. Okay, so e raised to x differentiation with the e raised to x, it is always e raised to x. Okay, so dt, t with respect to differentiation with respect to x, we write a dt by dx. Okay, so we want the value for dx. Okay, so take dx here, so we write dx e raised to x dx, which is equal to dt. So what I have done, I taken that dx, it is here to the other side, so e raised to x dx, which is equal to dt. Okay, what I have done, I taken a raised to x dx as a dt. So replace all these values in our integral. Okay, so what I'm going to write here, 1 upon d plus 2, this one keep as it is here. Okay, again integration of e raised to minus x, keep that term also as it is, because we are not going to change anything here in this e raised to minus x. We are going to keep that term as it is over here. Okay, because it is out of the integral, that's why it's none of our, it's not going to matter here to the integral. Okay, so integration, keep that one, e raised to x. So e raised to x we consider here as a t, so we are going to write as the e raised to t. Okay, that means e raised to x I consider here t, so this one is a e raised to t, and e raised to x dx. Now see that e raised to x dx can be written as a dt, can be written as a dt. Okay, now see guys how I have converted this complicated integral into the simple form, complicated integral into the simple form. Okay, so now it is easier to integrate e raised to t. Integration of e raised to t with respect to t, always e raised to t. Differentiation of e raised to t with respect to t, always t. Okay, so let's go for solving. 1 upon d plus 2. Okay, 1 upon d plus 2, keep this term as it is, e raised to x minus x as it is. Okay, this one is e raised to minus x, okay, as it is the term outside here, and e raised to t is having integration e raised to t. Okay, yes. Now but as we have all the function in the form of x, all entire function is in the form of x, then what that t is doing here, so replace that t, revert that t again back. Okay, so we know that t which is equal to e raised to x. Okay, replace the value 1 upon d plus 2, keep this term as it is, under bracket e raised to minus x, e raised to, what is the e raised to t, means we do not want that t, we want only the term in the form of x, so replace that t again back, revert it, so e raised to x is a t, then t replace here, we are going to write it as the e raised to x. Now see that I converted this one, this integral in this form. Okay, so actually don't go anywhere, this one is not a entire solution, remaining part it is also there. Okay, so let's go for the next part. Okay, so we have to reduce that 1 upon d plus 2 e raised to minus x into e raised to x. Okay, yes. Okay, so here I'm going to write the solution here, remaining solution. Okay, so what we have remain the values here. So the function we he left here with the value 1 upon d plus 2 e raised to minus x into e raised to x. Okay, yes. So we have to reduce this one into the simple particular integral. Okay, so apply 1 upon d plus a into phi of x, again similar process we have to repeat it here again. Okay, first of all write down the value for a. What is the value for a which is equal to 2 here. Okay, d plus 2 means d plus a which is equal to 2, and again we want the phi of x. So what is the value for phi of x? E raised to minus x into e raised to x. Okay, these are the a and value of phi of x we have here. Okay, replace this value in our given result. Okay, so that means we are going to write 1 upon d plus 2, we are going to write 1 upon d plus 2 into e raised to minus x into e raised to x as, now see that 1 upon d plus a and phi of x, it is the entire term, so e raised to minus x. Okay, e raised to minus x means e raised to minus 2x, a replaced by 2 only here, integration of phi of x. What is the value for phi of x? E raised to minus x into e raised to x. Okay, into dx. Okay, so phi of x, again this one is the value for only phi of x. We left here with the value e raised to ax, that means e raised to 2x. Okay, that means we write e raised to 2x dx. Okay, so don't get confused guys, I replace here only the value for phi of x, which is the e raised to minus x and e raised to x, and I kept e raised to ax as a e raised to 2x into dx. Okay, yes, this one is our required term. Let's go for the next step, e raised to minus 2x, integration of e raised to minus x into e raised to 2x. So whenever we have base same, we add their power. So e raised to 2x minus x, that means e raised to x, multiply by e raised to x dx. Okay, this one is the our required term left here. Okay, now see that we have to solve this integral further. As we can see that we have function to the power of function. So always remember guys, whenever you get such a function to the power of function, function upon function, or function multiplied by function, Okay, so in such a case, apply substitution method. So we are going to apply function to the power function as a t. So we are going to apply e raised to x, which is equal to t. Okay, I consider this one is a x, e raised to x as a t. So we have to replace dx also. We just not happy here with the value of e raised to x. We have to replace that e raised to x dx also. Okay, so replace the value e raised to x dx. Okay, e raised to x, differentiate both sides. E raised to x, which is equal to differentiation of e raised to x is e raised to x, and differentiation of a t dt by dx. Okay, so I'm going to write this one as e raised to x dx, which is equal to dt. Okay, I'm going to write e raised to x dx as a dt. So replace all these values in our given particular integral form. Okay, so next step, I'm going to write here e raised to minus 2x, integration of e raised to x dx is a dt. Okay, and e raised to x means e raised to t. Okay, integrate it, e raised to minus 2x, integration of e raised to 2 is e raised to t. Okay, okay, this one is our given integration. Okay, now see that as we have function in the form of x, that we don't want the t then. Okay, so replace t, revert the value for t from here. Okay, e raised to minus 2x into e raised to t means e raised to x. Okay, this one is our required particular integral. Okay, this one is our required particular integral. Now we are working here with the value of a complete solution or general solution. Okay, so complete solution or general solution, let me write here complete solution oblique general solution. Okay, we are working here with the value of complete solution or general solution. So I'm going to write y of x, which is equal to complementary function. So what we got, the complementary function c1 e to the power minus x plus c2 e to the power minus 2x. Okay, plus now we want the particular integral. This one is our complementary function. Okay, so we have to add here with the particular integral. So what we found, particular integral here, e raised to minus 2x into e raised to x, e raised to minus 2x into e raised to x. This one is our required complete solution or complete general solution here. Okay, now see that guys, how easy the example is. You will get such an example for 4 or 5 marks in your SPPU exam. Okay, I hope you all have understood this entire solution. So similar like videos we are going to continue in our next lectures. So if you want to see similar videos, go to my playlist and check all these videos there. Okay, so I'm going to upload similar videos daily in my channel. So I hope you all have understood my today's lecture. So thank you everyone. Thank you for my today's solution.